Okay, welcome back to 466 Logic Design, Lecture 3. And we still haven't done much with the astronauts, so we might start doing a little bit. So we're coming in about here with VHDL, right? We've probably got another astronaut out here, and he's coming in between the transistors and the machine code. Let's have a look at where we are. Just a reminder, I think everybody here is on the textbook, so please work through those. I had a couple of people talk to me about the chapters 1 and 2 being a little long, and they are, because a lot of the stuff in chapter 1 and chapter 2 should have been covered in 363, right? Some of it maybe wasn't, but a lot of it should have been. And that's why I've been getting you to do those 2 chapters. So we'll see. I'll get home, when I get home later this afternoon, I'll check in on the progress there for the week 3 participation. We'll see how we go. Well, that's where we are. The lab I want to do today, just going to grab one of these, is technically it's not going to use the board. Using the board, so let me just put that up on the video. So there's the board. Right. But I want you all to plug one of these into that, okay, during the lab. That's probably the better way to show it, like that. I'm going to get you to write some VHDL code today. So actually it's probably more like just cut and paste VHDL code or retype VHDL code. But I want you to get used to using Quartus and all the pieces of Quartus. So that's what I want to do in the lab today. So we'll see how that goes. Actually, another thing, I think there's a few board there, is one of these USB cables, and that's one of the older USB cables. It's got a really big sort of D-shaped connector at the end. The reason for that is those tend to be rated at a higher power than the standard USB micro connectors. And then the other cable is another USB cable, and it actually comes in 2 pieces. There's the USB blaster, and then it's got, and this is also an older style USB that plugs in quite way around. Right. Now the problem with these, this one, all it does is delivers power to the board, nothing else. So mostly forget about that, except it powers the board. This is the one that programs the board. And the trouble with this one is Altera, the people who make the Quartus, in fact it's Intel now, but it used to be a separate company called Altera, wrote a USB driver to drive that USB blaster, but they didn't get it signed. Right, so they didn't go through the process with Microsoft to get the driver signed. So we've had to get IT to properly install the drivers on each of these individual machines. Normally they could just flash it or put together an image and download the image and then that all works, but these ones, so one thing I want to check today is that those drivers are all installed. I've checked that machine, I've checked that machine. It looks good, but I want to check the other ones as well. Okay. There's our list of topics. So they're the accessible items. I will put in another plug for the MHRD game if you are interested in games at all. It's a little old school. In fact, it's so old school. I started getting flashbacks when the game started up, because the sound effects it uses when it starts up is the sound of an old boot up on a 5 1/4 inch floppy drive, not the 3 1/2 inch, but the big old ones, and it sounds exactly like the one of those old drives booting up. So it's pretty funny. Okay, I've been saying I'll give you some examples of project ideas, and I think I've said these boards, that little blue connector there that maybe you can't see from back there, that little blue connector, that's a VGA output. So you can display video. And the thought would be to write some sort of a game, maybe the old tennis game, the Pong game. You could implement that on the board. So that would be another idea. And the things I want to get through today, I do want to talk a little bit about VHDL before we get there. But I want to look at the solutions that I came up with for the Kano maps we looked at in the tutorial last week. I want to talk about the sequential logic solutions that I had a look at since last time we met. And then I want to get into Lab 3 and make sure you can all get access to Quartus on each of these, that you can program it using a very simple piece of VHDL. In fact, this one doesn't do anything. This less than equal sign is what you use in VHDL to assign a value to a signal, and this is just assigning the value of 0 to S. Lab 3 is about implementing a half adder in VHDL, right? So S is the sum output, C is the carry output, and this is telling us we've got A and B inputs. But basically I want you to use this as a template, and then you're going to have to change lines 7 and 8 to figure out what S is and what C is. You did this exactly the same thing last week in multisim, but I want you to do it in VHDL. And we might try and do a few other things like testing, figuring out how to set up a test within Quartus. And well, again, we'll see how far we get. I may even get you to do Lab 5 today as well. Lab 5 is basically just taking Lab 3 and making sure it works on the board. But we'll see how far we get. Okay, any questions from last week? About anything? Mostly okay? Yeah? Okay. So let's have a look. Okay. There we go. That's a bit better. Okay, so what I've done is for each of the x1 through x8, I've gone through and made my solution to each problem. Right, so let's just quickly have a look at this. I'll make that go full screen. Right, so here's x1, and oops, maybe got a, where's x1 gone? It was there. Oh, okay. That's better. Right, so the first thing you do is you take that truth table and you convert it, move it over into the Carnot map. And one thing I like to do to check that as a simple check to see I'm okay is I count the number of ones here. 1, 2, 3, 4, 5, 6, 7, 8. And then I count the number of ones in the Carnot map when I'm done. 1, 2, 3, 4, 5, 6, 7, 8. If those numbers don't match, then I've got a big problem. Right. And then the other thing is to make sure that each one goes to the appropriate place. So that 0 there is A and B and C and D are all 0, so that's that one there. Right? And then we can have a look at maybe 0, 1, 0, 1, which is that one there. Right, and 0, 1, 0, 1 is that one. And then maybe we can have a look at 1, 1, 1, 1. Right, so that's that one there. And what colour? Let's go with orange. And we can go with 1, 0, 1, 0. So 1, 0, 1, 0 is also 0. Okay? I'm not going to go through all 16 of them, but you can see how you transfer from one to the other. And then what I've tried to do is I've tried to find the biggest grouping of 2, 4, 8 or 16 ones, and then the second biggest, etc., until I have all of the ones covered. So here the biggest grouping is, remember the Carnot map folds back on itself that way, and top to bottom, left to right and top to bottom. So that grouping of ones that I've circled in blue is the biggest, and that ends up being B, D bar by the looks of things. And then in no particular order, the green one, the 2 ones down the bottom, the red one, the 2 ones up in the top right, and then the purple one. I've got one after those first 3 items. I've still got and let's go with light blue. I've still got this one here that is uncovered, so I need to find some way of covering it. And because of the top to bottom wrapping, I can group it with the one at the bottom of that column. and that's where I get the last B bar, C bar, D bar term. Okay, for this particular one, there's several, well, there's at least two answers that would be correct for this one, right? Another thing I could have done is with this green one here, if instead of that green one, so this term here, I could have circled those two, and that would still give me a minimal coverage, but instead of that A, B bar, C bar term, it would get me A, and then it's C bar, D bar, right, because it's in that 0, 0 column. And that would also be a valid answer, right? So just because my answers may not line up with what you got, doesn't mean you're incorrect. I've just given one example of a minimal covering in each of these. Okay? So I don't know whether you want me to go through each of these in any detail, but there's the next one. And yeah, I'm just seeing if there's a yeah, so here instead of well, maybe I do need to do that. I'm just trying to think if there's another thing I could have done in covering any of those. I don't know whether there is. Oh, I could have, yeah, I could have, for the, I think it's the red one here. Right, for the, is that it? A bar B C, right, instead of the red one there, I could have done that, right, and that would be, instead of that term, I'd get a plus A bar B, and that's D bar. Right. So I just replace that A bar B C with an A bar B D bar, and that would also give me a minimal covering. I can't use both. Both would mean I'm including more terms than I need to, so it wouldn't be minimal. Not quite sure why those are going away, but anyway. Right, so there's the next one. This one was a bit hard because I had to include 2 4-variable terms, right? Because the 2 ones in the 1, 1 column are by themselves. Now, you'll notice those ones in the 1, 1 and 1, 0 column. So you'll notice, where are we? Let's grab that one. You'll notice these here, and I haven't found a good explanation. In fact, let me write down that as something that I should do. I haven't found a good explanation for how, instead of from a Carnot map pulling out SOP terms, right, sum of product terms like these are, being able to use exclusive OR, right? Because those 1, 1 and 1, 0 columns, where they're diagonal like that, that is usually an indication that there's an exclusive OR operation happening. And because if you go to right, if you go A, B, and you try and put in, which I could write, that would be wonderful. Right, so 0, 1, 0, 1. Then the exclusive OR operation, so A exclusive OR B, is like that. Right? And it's a bit hard to see, isn't it? I should have used a different colour. Oh well. Let's see if I go over the top of it, if that makes it. No, that doesn't work. Sorry about that. Let me try just a thicker pen, maybe. Right, so there's an A, that might look better. And there's the B. Right, and that comes up as A. That's what the A exclusive OR B two variable Carnot map's going to look like. Right. And because that pattern is showing up in the 4 variable Carnot map, I suspect there's a way you can derive maybe a simpler expression. It's not going to be a sum of product expression, but it's going to be a simpler logic expression that involves exclusive ORs. Okay. So there's that. That one was relatively straightforward. Just trying to see if there's another way I could have arrived at the same thing. I don't see anything where I could replace one of the terms I got with a different term and still get a minimal covering. Don't know about that one. Oh, this one I could have, instead of the that purple one there, this one here, the what's that? That's A C bar D bar. So instead of this term, I could have circled it that way, right? And that's going to be an A B D bar. And I could replace that A C bar D bar with an A B D bar. I think I did X6 last time, and that was kind of funky, because you still need 5 terms, but you only need 2 variables in each term. And there's X7, just need the 3 pieces. And instead of the blue one, where's it? Instead of that blue one, I could have done that instead, right? And that would be A bar, B bar, and that's D. So I could have replaced A bar, B bar, C bar with A bar, B bar, D. And I think that's about it. Okay, and that's X8. Any questions about any of the Carnot maps? No? All good with that? Does everybody know how to do a 5-variable Carnot map? Right, these are 4 variables. How do you do a 5-variable or a 6-variable Carnot map? Let me see if I can pick on someone. Is the right class? Fahim, how do you do a 5-variable? How would you approach doing a 5-variable problem with?
I have done only 4 variables. I never have done 5 variables.
Okay. And Charles is here. You got Michael P. Yeah.
I'm guessing you have A would be on the left still, how it is. But then you would have C, D, E across the top. And instead of it being two values, it would be 0, 0, 0, 0, 0, 1, 0, 1, 0.
Yeah, you could do that. That's actually, I haven't seen that done, but that's not a bad idea. The trick though, right, and you sort of see it here, is to make sure you get the counting right? Because it's very important that each column only changes by 1 bit each time, right? So if you were going to extend this to, 0, 0, 0, 0, 0, 1, then you'd probably have to, well, I think it makes sense to kind of do that, right? Have it look exactly the same as the original one, but then you want to keep counting and get something like 110 maybe, and I don't know then if you want to go to 111, and then maybe, I don't know, 101. I'm not sure what the right sequencing is going to be, but you could still do. The way I've seen it done, right, is for 5 variables you just have 2 Carnot maps, and if your 5th variable is E, the left-hand one is E, and the right-hand one is E bar, right? And then you can, if you've got ones in the same spot in both the E and the E bar, that means that E doesn't matter, right? So you'd have, basically you'd have, right, A, B, C, D, and that's the E one, and then you'd have another one here. Which is what happens with E bar. And then the 6 variable one is the same thing again, except you now have 4 variable Carnot maps. And so you've got on this side, this would be F, and then you'd have another 2 of them down here, which would be F bar. But you could take your idea and go extend it with 3 digits instead of 2. Okay. Okay. Let's. Everybody okay with Carnot maps? No? It should be reasonably okay. Let's go back here and have a look at the sequential logic. In fact, before I go there, let me just fire that up and get on to the CET, the SEST desktop. We should start up here. There we go, desktop. Okay, hopefully that'll be started up by the time I need it. Right, so the other tutorial we looked at was, let's change the date. Was this one, and the idea was to, let's put it into a window. The idea was to be able to count through an odd or a non-sequential number of bits, right? So it's sort of a grey code. You can see there's only 1 bit changing between each subsequent state. And then I talked about 2 ways of doing it. One using a D flip-flop, and then also using a JK flip-flop, right, for the state. Remember, there's 8 states, so we need 3 bits to represent 8 states. And so that's what we've got here. Okay, so here's the, I should have done a different colour. Oh well. I wonder if I can, use black, dark mode. Colour. Dark mode. Let's try dark mode. That might be better. I don't know, is that any better? No? Let's try that again. Let's go back to the other one. Light mode? Yeah, I think that's a little better. Sorry?
Turn off the lights.
Turn off the lights? I just want everybody to go to sleep.
Just one set.
There we go. That might be a little better. Okay, so here is the present state, next state table, right? And what I wanted to figure out is for each item, so for each, let me just put that up in full screen. Right, so for Q3, here, the transition is going from 0 to 0. Right, so what I need to look up is the D flip-flops excitation table that says, okay, in order to get a transition from 0 to 0, I need to make D, the input to the D flip-flop, be 0. Okay, so that's where that one comes from. And let's just try a couple of others. So for let's go with this one, right? So this is Q2, and Q2 transitions from 1 to 1. So in order to get Q2 to transition from 1 to 1, I need to make it give its input, its D value, to be a 1. And let's try Q1 somewhere, maybe. Yeah, let's try Q1 here. Is going from 1 to 0. Oops, sorry. That one. Q1 is going from 1 to 0, and that tells me that the D, which I highlighted first, should be a 0. So I can go through every transition in the present state, next state table, looking at the D flip-flop's excitation table, and I can figure out what D has to be for each present state in order to get to the next state. Right, and then all I have to do is take that D3 column, for example. So let's go with light pink, maybe light pink. Right, take the D3 column and move it into a Carnot map with Q3 on the y-axis and Q2, Q1 on the x-axis. Right, so for example, this 0 is when Q3, Q2 and Q1 are 0, so that 0 is that one there. And let's try this 0. It's a bit thick, oh well. And that's when Q3 is 0 and Q1 and Q2 are both 1. So that's that 0 there. Right? So I've moved the D3 column into a Carnot map. And then I've done logic minimization on the Carnot map to tell me that D3 is equal to Q3, Q1 or Q2, Q1 bar. And then I've done the same thing again for D2, for the D2 column. Right, so I can take that D2 column and move it here and do logic minimization on it. And then I can do the same thing for the D1 column and do logic minimization on it as well. Then and I apologize for my drawing. Then I can figure out how to make the circuit count like that. Right? So here are three D flip-flops. Right, so my, where are we? There we go. There's my D2. Right. And there's my D3. And I didn't colour in D1, so let's give it a colour. I don't know. Alright, so there's D1 and there's my D1. And then I can put that together. Now I've got a few things missing on here that need to go into multisim, but that's pretty much it. One of the things that's missing is I have to give each of these a clock. D flip-flops and JK flip-flops are, at least as far as their D inputs are concerned, are synchronous. Synchronous means changes only happen usually on a clock transition. Usually it's either a positive going edge of the clock or a negative going edge of the clock. In this case, I've labelled the clock as just CK. That usually means it's a positive going edge. If I'd labelled the clock input as CK bar, that's a negative going edge. Negative edge trigger. Okay. So let's, I went ahead and implemented that in multisim. Let's see if I can fire that up and open it up. Where did I put it? There we go. So there's my D flip-flop. Right, so let's just get that out of the way. That should show me everything. Right, so there's my implementation. And I didn't do anything particularly fancy. I just, each of the terms going into D was Q or Q bar or some other Q and some other Q. Right? So I just used two AND gates and an OR gate on each input. And that works. And I've got my clock here. I've set the clock to be a 3 Hz clock going, and the same clock is going into each clock input. Now these flip-flops have a clear and a set input. Right? Those inputs on flip-flops are generally asynchronous. So they happen regardless of the clock. I don't want to be able to set or clear any of the flip-flops in this example. And when I first ran this, it all worked without having anything connected to those inputs. Another way to check to see that it's an inverting input is there's a bubble on the input, right? This is actually a clear bar and a PR bar input. So to make sure that reset wasn't happening, I put on the VCC, right? I put on this voltage, and I connected that voltage to all of the unused inputs. They're all active low inputs, so if I tie them high, they're always going to be inactive. Okay, and then I can run that maybe, and you should see the lights turn on and off in the appropriate sequence. I've labelled them as Q3, Q2, and Q1. Okay, so it counts through the sequence that we're after. Any questions about that one? Okay. Let's go back here. So I also did a design for, let's make it bigger maybe. For the same problem, but this time using JK flip-flops. Right? And at first glance, this looks more complicated, a solution, right? Because I've got now 6 variables that I've got to figure out instead of just the 3, the D inputs. I've got J3, K3, J2, K2, J1, K1. But the nice thing about JK flip-flops is that their excitation table has a lot of don't cares in it. And don't cares are nice because I can use them or ignore them depending on where all the actual ones are. Right, so here, let me grab that one. Right, so here I can grab that X and get some simplification. Here I can grab that one. This one's a bit more complicated, so I can do that. Here I can do that. Here I can do that. And again, this one's a bit more complicated, so I can do that. Now, one thing I noticed is this, again, this diagonal structure, right? And I thought, oh, I wonder if I can write this down as an exclusive OR. And it turns out for both of these, for J1 and K1, I can write it out as an exclusive OR. Right, so the implementation, and again I've left off the clock, I've left off the reset set inputs, but the implementation now has 1, 2, 3, 4, 5, 6 gates, external gates, compared with 1, 2, 3, 4, 5, 6, 7, 8, 9 external gates. Right, so it's, even though the design was a bit more complicated, the circuit I ended up with is simpler. So that's often why things like JK flip-flops are preferred compared with Ds or T flip-flops, because of that those extra don't cares that help you with the simplification of the external logic. Okay, and then again I opened up no, other way, sorry. I did an implementation of again the same counter, this time using JK flip-flops, and again I had when I first did this one, it didn't work at all because I didn't connect up the clear and PR inputs to VCC. There's VCC up there. When I first did it, it didn't work at all, and I had, for this one, I had to go back and connect up VCC. So I did it on the D flip-flop implementation as well, just to remind you. And again, this one runs and it seems to do the right thing. Okay. Any questions about that? Okay. So let me get out of here. Go back here and I'll turn the lights back on. Maybe. Oops, wrong one. That one. So you may know that I grew up in Australia, you probably tell from the accent, right? And one of the things that I still can't quite get used to are these things. In Australia, that's all. So normally I'm used to turning lights on just by going down like that, but here it's the other way. So, and it was funny. Well, we're all standing on our heads, aren't we? Right? It's the other side of the planet. The other funny thing about that is, at one stage there was a power outage, and it wasn't going to be fixed until whenever. I hadn't realised that the only light switch in my house that is not done like that is the light switch in my bedroom. So I thought I had turned the main light in the bedroom off because the power was out and I wanted to go to bed, so I turned all the lights out. Of course, the power came back on, and apparently whoever had the house before us had mounted that particular switch upside down. So I turned it on. So I woke up at about 3 a.m. with the main lights on, which was I just hadn't noticed that that particular light switch was the wrong way around. Anyway. Okay, let's see what else. So I thought it might be entertaining. I've shown two ways here of solving this problem, right? This bizarre counting problem. I think I mentioned last week another way to do it. Do you remember what that other way to solve the problem is? Anybody? Let me grab my phone again. Right. Do you remember what the other way of solving the problem was?
We're talking about flip-flops.
Right. Well, it's the same problem, right? So if there was another way to solve it other than this way. Sorry? SR? Okay, yeah, we could use an SR flip-flop or a T flip-flop. Yeah, we could use another sort of flip-flop. But there was another. It would involve a different design approach. And we get Michael. Michael, yeah?
I do not remember.
Don't remember? Eric?
The decode variable state.
Right, decode, yeah, exactly. So to unpack that, right, so another way to do it, and let me choose something that's, maybe that's okay. Yeah, that's okay. So remember the state transition diagram we had at the beginning, right? Let's try that again. Probably should just redraw it, shouldn't I? There, whoa. It changed. How did I do that? That's interesting. Means it is possible to change pages. Right, so there's the state transition. And what the design approach I took here is to force the state to go in this order. Right? That was the design approach I took. But the other way to do it, I can scroll down, probably should do a. The other way to do it is to just have a standard counter, right? So a standard 3-bit counter. 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So there's just a standard 3-bit counter. And then the trick now is to be able to give an output. Let's just make that a bit thinner maybe. The trick now is to be able to give an output that matches our counting. And I've forgotten the ordering. 0, 0, 1, 0, 1, 1, 0, 1, 0. 110, and then 111, I assume. And 101, and then 100. Okay. So that's the trick. And so then what you get is right, we have our Q3, Q2 and Q1 and our out, we'll call it, I don't know what to call it. O and Q look too similar. Let's just go with O. Right, and we've got 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and our first, let's get that away. Alright, so 0, 0, 0, 0, 1. Oops. So that's 0, 0, 0, 0, 0, 1, and then 0, 1, 1. And then 0, 1, 1 gives us 0, 1, 0. And then let's just keep going with these. That's 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So that's 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0. Okay, and now we can put together a Carnot map for O3, O2 and O1, just pulling off the our normal counter bits. And that will also get a implement a counter with the same with the old sequence. But our basic thing, the nice thing about that is we can just use either the counter for a just using flip-flops is easier, or I don't know whether I've got it here. It's not there, so let's go here. The 74LS 90. 74LS 90. What we can do then right is there are things that are just 4-bit counter chips. In fact, this is a decade counter, so it's a 4-bit 0 to 9 counter, and we can just use a single chip in place of those 3 flip-flops and all the circuitry to get it to go. This is a decade counter though, it doesn't count up to 8. Right, so what we have to do is we have to get it to reset if it tries to get to 8. So there is a little bit of extra circuitry required. But then we can get it to it's just a bit of a different approach. We're just buying the normal counter off the shelf. There's this one, I think there's a 74LS 163 as well as another one. Yeah, it's a standard 4-bit counter though. go. So it's a counter that you can load up values into. So you don't have to start from 0, you can start from some predefined number. But again, the aim is to find just another way of implementing that counter. Okay, as is usual, I've been talking for about an hour, so I'm going to take a break. Michael, you have
So I do have a question. So why on the left it counts from 0 to 7, but on the right it's all over?
Well, because where we started with this question was the counter was all over the place, right? The thing we're trying to implement is that counting sequence, right? And it is all over the place. So the right 0 0 0 0 0 1 0 1 1, that's going 0 1 3 2. What's that? That's 6 7 5 4 back to 0.
But why is it like that? But why is it that way?
Why is it that way?
Why?
So the reason I chose this particular example is because it's it's not quite a grey code, but it's a sort of code that counts by only changing one bit at a time. Okay? Normally if you count, if you go from 3 to 4 in binary, it goes 0 1 1, and then 4 is 1 0 0, so all 3 bits change. This particular count is an example of a grey code counter where only one bit at a time is changing. Okay?
So it changes.
That's why I chose
it. Changes at a time.
Yeah, exactly. Each transition only changes one bit. Okay? That's why I chose the example.
So,
That answer the question?
Yeah.
Okay. Okay. So I'm going to take a 10-minute break, and when we come back, I'm going to ask you to think about implementing this, but I'll give you the parameters of how I want you to think about implementing it. Let's go for a break first. And I'll just put up a 10-minute counter. There we go. Okay, let's go back to it. Don't do that. So, how many of you have done some programming? Hoping everybody has, right? So, what I want you to do is I want you to think about, in whichever programming language you have some familiarity with, how would you write code to implement this counting sequence? Can you spend, I don't know, 5 minutes trying to write some code that would implement that counting sequence? So let's just put a 5-minute timer up. And think about, so maybe I shouldn't put the counting in full screen. Let's just see if I can show both on the same screen at the same time. Right, so there's my counting sequence, and there's the 5-minute timer. So have a think about how you would write that in C or Java, or I don't know, does anybody write in Forth or C#, Python? Any of those would be fine. got about a minute to go. Okay, let me pick on somebody. Mohammed, how would you go about it?
You make a list.
Make a list?
I see there's a pattern. So it's the list, and then Java has this repeat the pattern.
Okay. Right, so that's certainly one way to do it. You could make a list containing 0, 0, 0, 0, 0, 1, 0, 1, 1, put those things in that order, and then you could just keep cycling through the list, and that would certainly do it. See if somebody else has Anas, any thoughts? No? Matt, any thoughts?
Not really.
Not really?
Yeah.
Okay, Emily?
I was thinking in terms of like Python, like I can do the numbers like in the range just because they're only 0 and 1s, and then I could write out the sequence, how it is, and then print whatever sequence.
Okay, yeah, you could do that. And last but not least, Michael, any thoughts?
I'm not sure.
No? Okay, so the main thing with that you've got when you think about programming language, there's two. One of them is data representation, right, the list. The other one is the programmatic structure, like a loop. Right? They're the two things that we've got to sort of build from the ground up with flip-flops and bits and that sort of thing, that we've just got immediate access to in C or Java or Python or any of those languages. And with some gotchas, with some caveats, VHDL is a programming language, right? So we do have some of those built-in nice functions. We can have arrays, we can have loops, but we can make it all hang together and run on hardware. So let's quickly go back here. Okay, so VHDL. I'm wanting you today. I want you to do Lab 3, but I want to talk a little bit about VHDL first, and I want to talk a little bit about quarters. So let me just fire up quarters because it might take a while to start up. So the first thing you've got to first structure that you've got to come to grips with in VHDL is the entity. And the entity, really all it does is describe what a former professor of mine used to talk about as the gazintas and the gazoutas, right? The stuff that goes in and the stuff that goes out. And that's all it does. It doesn't tell you anything about what the inputs do and how they interact to get an output. All it does is it describes the interface, the ports. And that's the first thing when you're making a device in VHDL, that's the first thing you've got to think about. What are the inputs and what are the outputs? And then the second piece is the architecture. And now we take that information, the inputs, from the entity, and we decide how they interact to produce the outputs. So that's the system behavior. So they're the two pieces. So if you have a look at, let's just quickly go back to, I don't know if I've got that open. Let's go to Blackboard. There's always the problem of that the cell phone coverage down here isn't the best. Sometimes that doesn't come through. So there's a whole series of screenshots showing you how to start up quarters, which I'm not going to go through just yet. What I really wanted was something like that. Yeah. So here's an example, and I've just called it Lab 3, but this is going to be a half adder. And here's the definition of the inputs. Note the keyword in and the outputs. Be careful with some of this. Let's just go here. And I'm just going to put a lab 3 here. No, didn't want to do that. Sometimes it lets me do that. Yeah. For some reason it's decided to get the text. So just be a bit careful with what I put here. Bit is a standard VHDL type. It's a little limited though. And I'll talk a bit more about that. But the key piece here is that we've got our inputs, A and B, and our outputs, S and C. Remember from the previous lab, lab 2, right? We had that relationship between the inputs and the outputs. We had that truth table. So now here, there's the entity, and here's what it does, the architecture. In this particular set, nothing's happening, right? The S is always 0 and C is always 0. But if we remember, right, here we had S equals A exclusive or B, and C equals A and B, or just AB. Okay? So what you should be able to do is change those two lines to be just A, X or B, and A and B. So there's a few things I'm doing there, right? The first thing is this less than equals is the assignment for signals. A, B, S, and C are all signals. I cannot assign anything to A and B because A and B are inputs. I can assign something to S and C because S and C are outputs. Right, I'm depending on A and B to come from outside my entity, so I can't overwrite what the outside is saying. Okay. What I thought I'd do quickly is show you how I want you to do the lab, and we'll see how far we get. Okay, so there's quarters. Okay, and I think the easiest thing to do is to just click on New Project Wizard, and then it'll go there. and I like to put maybe on OneDrive, maybe not. Yeah, let's put it on OneDrive. That's my personal OneDrive. It's not mine. I'm just going to put it on my documents folder, and I'm going to make a new directory. Oh, there is a 466 directory, and I'm going to make a lab 3 folder. Just so that everything's, and I'm going to call it lab 3. And notice, so the name of the project is this one, and then it's asking what is the name of the top level entity. That's so you've got to be very careful when you write the VHDL code. This name here has to match the word after the keyword entity. Right? So that's why here I've put lab 3, lab 03. Okay, you can change that. It doesn't have to be lab 3, it could be anything. But just to be aware, I'm just going to say an empty project. I don't have any files yet, so I'm not going to add any files just yet. Now, I've only installed the Cyclone 4E and Cyclone 4GX devices. On some of these machines, there'll be a much bigger list. Make sure you select 4E. That's the name of the chip, that's the family that this chip belongs to. Okay, so Cyclone 4E. Now, I've got to remember exactly which Cyclone 4E it was. I seem to recall, let's just see if I can pull it up here.
CPC8.
It's a C8, is it? Yeah. So select that one. I think it's in the lab sheet, but I have forgotten. Let me just quickly see if I can find the lab sheet. EP. Yeah, there we go. It's EP 4C E6 E22C8. EP 4C E6 E22C8. Okay, we'll do that. Now this one, I think there's something we've got to select here. Yes, I said to just go with the defaults here, but don't. Under simulation, select Model Sim Altera. You can fix it later, so it's not a big deal, but it's just easier if you do it now. And then the format you want is not Verilog, it's VHDL. Okay, so I might just edit that in the lab. and then it's just giving me a summary of everything, and I can say finish. And my laptop's a little underpowered, so let's just give it a minute. Okay, so there's lab 3. Now up here, remember I told it that the top level design entity was lab 03. That's that thing there. Normally, if I click on that, it should open up the implementation, the VHDL file. I haven't added any VHDL, so it's giving me an error. It can't find the design entity. So let's make a new VHDL file, right? You can make new lots of things, but the one we want to make is a VHDL file. And I'm just going to make sure that that's there, and I'm just going to check what I've put in there. So entity lab 3 is, and then end entity lab 3. And I'm just going to relabel that as, well, it's already automatically relabeled it as lab 3. Right. And now if I double click there, it'll open up straight into the VHDL file. Right, I haven't put in everything I need to here, so I need to say port, and then the inputs, AB. Now, I mentioned bit before. I'm going to ask you to not use bit. There was a bit of work done to improve how VHDL works, and I want you to use a type called std logic, STD logic. Now, std_logic is not standard VHDL. In order to use it, you've got to do a few other things. Let's go there. One thing you've got to do is, just like in C or C# or Java, you've got to do or Python, you've got to import. The import statement in VHDL is library, and the library you should use in every one of your VHDL files is IEEE. And then there's a particular part of that library I want you to use. And where is it? IEEE dot std logic 1164, and then it's .org, I think, yeah, .org. Now notice one thing I'm doing. Let me just see if I can make the text a little bigger. Maybe preferences. Just so you can see it, maybe. Sorry, I just thought there it is, options. Fonts. It did that, but it didn't do the text. Okay, let's try that again. Tools, options, VA tool options, fonts, text editor fonts is the one I want. And again, let's go with 14 point. And it's too big, can't see it. I can't get down to the button. Is that not auto hide? Let's see if that works. Probably not. Okay, is that okay? Yeah, that's a bit bigger, so maybe you can read it a bit better now. Okay, so notice I'm ending each statement with a semicolon. Make sure you end each statement with a semicolon. Even within the port statement, I've ended the list of inputs, or at least the list of inputs with the same type, with a semicolon. And then SC are outputs, and they're also type studded logic. And I think that's all I have to do with my port statement. And that's the end of my entity statement, which I also have to finish with a semicolon. And then I can do my architecture. And you need to give a an architecture name, and then it's implementing the lab 3 entity, right? So this is saying this is the name of what's in here, and the way you get into and out of it is through the lab 3, and then is, and then I'm just going to then you've got to do a begin, and then you do an end architecture lab 03 arch. I think that's it. And then I like tabbing. So as I said, I think it's A XOR B. You will notice that the keywords, exclusive OR, get highlighted in red, studded logic. And then the carry bit is just A and B. Now I should just be able to go here and say start. And what you should see, which you did in the first lab, I think, is it should compile those things. And again, mine is a little slow. Actually runs quite a bit faster on the desktops that you're going to be using. hoping there are no compilation errors. So the output can sometimes be useful, particularly the error, if there are errors. Okay, it's done the analysis and synthesis part, and now it's looking to place things. Now, one of the things I haven't done yet is, even though I set it up, the project up to use that particular chip, I haven't told Quartus at all how to connect up A and B to the hardware, or S and C to the hardware. I still have to do that. Okay, so here's a warning. Some pins have incomplete I/O assignments. It's not an error, but it is a warning. Okay, and now everything's green. It all worked. It's not going to do anything, right? If I try and deploy that to the board, because there's no connections between A, B, S, and C and the actual pins on the board, it's not going to work. But at least it'll, at least it's compiled. So how do we do those assignments? Well, we go here and we open up the pin planner. Right, and the pin planner, provided we will tell you A, B, S, and C, and whether they're inputs or outputs. And we've got to give it some numbers in here to do the connection. Now, best way to do that, let's go there. Right, this GitHub repository, which I believe is linked to in the notes, has this table, and this table has the pin numbers for the keys, right, on this board. If the 7-segment displays are at the top, immediately at the bottom from the 7-segment displays there are 4 push buttons. Those 4 push buttons are on pins 88, 89, 90 and 91. The other thing this I/O or this pinout has are the pin numbers of the LEDs, right? LED 1 through 4, and just to the left of the switches there are 4 LEDs. Okay, so that's these pins. So let's just connect up the inputs first. There we go, that's got everything on the screen that I need, I think. So there's that. And let's go back to the pin planner. And so the keys I want key 1 and key 2. So that's 88 and 89. So 88, pin underscore 88, and pin underscore 89. And then I want the outputs, I want the LEDs. So let's go with 87 and 86. Pin 87 is C, and pin 86 is S. Okay, so now I have the code connected to the real outputs here. Okay, so that's kind of nice. Now the problem I have is you will notice, because I've changed the pin assignments, all my lovely green here has gone away again. That's telling me I need to redo the compilation. So looks like it's saved, and I'm just going to restart the whole compilation. I suggest restarting the whole compilation just in case, and it'll probably take a while again. While that's happening, let's talk about bringing the board up. First thing you want to do is take that single piece with the D connector on one end, USB cable, plug it in to one of the USB ports on your computer, and for some reason that one's always a pain, and then look for the big red button, and it's if you've got the 7-segment displays at the top, the big red button is on the top left, and plug in that and you'll see it powered up already. I'm going to turn it off. Right, the red button turns it on and off. Let's see if I can show that. And it's funny, I think I forced this one to have a more useful program on it, because you can actually see things happening with this one, right? The LEDs are changing. Then turn it off, because I'm going to want to plug in the second one, right? So I'm going to plug that one in. You just heard it detect that, right? So that means there's a separate driver has to be loaded. That's one thing I want to check during today's lab, that all of the machines you're going to be working on, right, will load that driver correctly. And then this ribbon cable can plug into 2 places on the board. I want you to use the JTAG connection. And that's the one, again, if we've got the 7-segment displays at the top of the board, the JTAG connection's the one at the bottom. You can program the board either way, using either JTAG or AS, the serial connection. The difference is the JTAG programming is ephemeral. If you power down the board and power it up again, the program won't be there. But if you program it using AS, it'll be there again once you power cycle the board. Okay, so JTAG is really, really useful for debugging, right? Because you can keep loading different programs up again and again and again. Whereas once you've decided what you're going to put there, you can blow it using AS. Okay, now I'm going to turn it on, And you'll notice, if we scroll this down maybe I'm going to scroll that one up. Down the bottom here, there's an option that says Program Device. If you double click on that, it will bring this up. Now, I've already run this on my machine, so it knows about it. What will probably happen to you is up in this box here, where it says Master USB 0, it'll probably say no hardware. Okay, so what you've got to do is you've got to click on Hardware Setup, and then instead of selecting no hardware, select USB Blaster. And then hit Add Hardware and then close it. Okay? And once that's done, I should just be able to hit Start. And even the window's a bit small, but you should see a green 100% successful. And now I have a slight problem, right? You can see there's already an LED on. But if I press one of the buttons, that LED goes off and the other one goes on. If I press the other switch 2, same thing happens. If I press both of them, I get both LEDs on. All right. Any idea what's happening? Well, for a start, is that the right thing? No, you're right, it's not the right thing. Any idea what could be happening? Here's my pick on a student out. And we're back to the beginning again. Eric, what's the, any idea what the problem is?
I honestly don't have any idea.
Don't have an idea? Anas, any idea?
It could be that it's like the natural state of that device when you click the button and the switches as the software is not loaded into it. So the function is not.
The function is there.
The function is there.
Yeah. But it is to do with the hardware. The issue is, and it's so the issue is I made an assumption, right? I made an assumption about the switch being open, me not pressing it, is a logic 0, and me pressing it is a logic 1. That's a wrong assumption. Okay? The correct assumption is that me not pressing it is a logic 1. Well, it means that the inputs are active low. Right? And I believe the other problem is the outputs are also active low. So everything's the logical not of what I think it should be. Anyway, the aim for this lab for you is not to get it programmed. That's lab 5. The aim for this lab for you is to be able to get it compiling in Quartus, and I also want to check that all the machines you use have the drivers loaded. Okay, so I want you to get the compilation, I want you to go to Program Device, I want you to hit Hardware Setup and make sure you can select USB Blaster. Any questions? Okay. There are boards over here. So come grab a board and take them to one of your machines and try and do that through.
Professor, since I'm using my laptop, would I need to install any drivers?
Possibly, yes. But if you've installed porters, then the drivers come with porters. So you should just be able to navigate to the porters drivers subdirectory and when there's a problem. Okay. So the lab write-up should let you, have you screenshot everything that I just did. So feel free to go through that. Right, so I just pulled up the schematic for this board, and let's have a quick look. Here are the LEDs, and here are the pin connections to the chip, right? So in order to turn this LED on, this side of it's connected to 3.3 volts. In order to turn LED 4 on, that line has to go to 0. right? So turning it on is 0 volts, which is active low. Right? Same over here. When you press the switch down, it grounds the input through a smallish resistor. So again, the inputs are also active low. Right? So when you press down, that's not a logic 1, that's a logic 0. So that's why it's not quite behaving the way I expect. Okay. Thank you. I'll be right back.
Okay, so if you go to assignments, and then pin planner, and there you'll see pin publicity number. They're the numbers you want to use. Have a look at the data. I just want to see that you can attempt to program it. So if you want to try and push back to the board, that you can do that. You need to compile it. It hasn't compiled it. Right, so it'll show you on it. Yeah. Okay. Okay, no worries.
Okay, let's compile. Let's try loading it to the board. Okay, and now somebody's looking over your shoulder.
Exactly.
It either stops working or starts working.
Exactly.
Depending on. Thank you. You're welcome. Right, so this is the sun equals the sun is that, and then you haven't told it what time the output is. Right, so you need to add what's the title of the reference? Okay, what's up, Michael? No, just you should all connect up. No? Okay, that's all good. And you've got two other things. That's right.
You say you want about 16
Well, you want to do something else, right? Because you want to implement this as a, so you want the sum. The sum is a exclusive or B.
Oh, yeah.
And the carry is a n. Okay. So let's just check that that compiles first of all.
So I just need to change that to exclusive or that's the same thing, right?
Okay, so that's what I was demonstrating. Got both of them plugged in, right? So you go down here and you open the program and
It's a dark one. It's around. And then you should just put all the numbers.
Oh, you're stuck. That's what it is.
Something is not right.
What's the directions?
No, well,
See, I haven't seen that oh, this is
Maybe I've been having new issues. That might not be right as well. It may be this cord with,
could be.
the swap it, and then just power it.
Yep,
and then
yep.
just
Try that. Try that.
turn it so.
Is that what we're supposed to be putting in?
It's something else. Try just try one.
I just put an X on,
Yeah. So A
X
or B.
yes.
and then
Yeah, I don't want to put it to.
yeah.
and then I'll get I'll just at the back. It's like okay. Here's how they different. Well, because you're not telling it to them. Right? That's just setting S to 0 and C to 0. So you need to change it to match the truth statement, right? S is A, X or B, and C is A and B.
So I should switch this to one.
Well, they won't do anything unless we connect it up to something.
Yes.
Yeah. So it's
Just those two examples. Looks good.
Yeah, if you just open up the program. Oh, that's good. Yep. Okay, that's all. So, if you want to, it's okay to do the right file.
Oh, yeah, it's just a screenshot of the this one. Just a screenshot.
Top left.
Oh, yeah.
Just right in
So I
the
want
right
to see the
in.
VHD file.
It should
And
be.
then so you can automatically upload the whole project.
Oh, that's the other one, so that one first.
Just give you a question.
It just works, bro.
I guess connected and it's not fulfilled. Is it working on that? How do you go about Sequential Logic?
You said what?
Can you tell you how you go about
So,
Yeah. Screenshot of that. On the connection. Specific piece.
so you turn it on. And then scroll down the section to program device. Since there's no hardware on this side, and then select under hardware.
Yeah, or just, or you can just,
Or either.
just use the combo box at the top. So where it says no hardware, just go down. And then Yep.
It might just be my laptop. Or the whole West.
I would suspect it's the other one. Yeah.
Or the drive.
Compilation form of the code and then that was the compilation.
Gotcha.
Replicate everything on PC.
Yep. Sorry about that.
No, it's not.
Do you want us to upload this file onto this? Or?
So the main thing I want to see is that it's compiled, and I want to see the VHD, so it's the right thing. So that's telling me it's all compiled, and that's telling me so that's screenshot. Yeah. Okay, most people seem to be mostly done. Thank you. I didn't hear anybody not able to do the USB blaster. That's the main thing I wanted to check. I'm going to take another 10-minute break, and I want to do a quick demo when we get back, and then it should take half an hour, so we should be done by the 12:30. Okay. So I'm going to take a 10-minute break, and we'll be back.
Do you want these backup?
Yes, so once you've finished, can you pack up the boards again? And maybe, so as not to annoy Michael P, just put them on the desk here. So just put them on this front desk once please, if you've got an anti-static bag, please put the board back into the anti-static bag and put everything, the 2 cables and the remote control into the box.
I think he wants the screenshot of the other. Not this one.
Sorry?
So he got his board to work.
Yep. So all I want you to do. That will do. I actually want to see the VHD code as well, so yeah, so if we could do virtually the same thing, but with that that's all.
So I don't need the screenshot of this, just the code.
So just the code and having it compiled.
Okay.
No. Way. Wasn't that one of those things? Was it really?
Okay. So, hopefully everybody got that done. The main thing I want to see is your code, and if it's possible, I don't know whether I can show it here, the fact that you've got all green ticks so everything compiled. I don't need to see that deployment to the board. That's okay. We will get to that, as I said, in Lab 5. So I showed you that, where is it? I put it in there, right? So the LEDs are active low, so I need to pull LED 4 down to ground to make the LED go on. The switches are also active low, so when I press the switch, the input goes low. So when I don't press the switch, the input is high. That is a little counterintuitive. To make the way the board works more intuitive, and it makes the code uglier, I've inverted all the inputs. So wherever I had an A, I put a not A. Wherever I have a B, I put a not B. And whenever I send something to the output, I invert it as well. Right? So not. It's the same thing, but now I'm converting the logic to something that looks to me more logical on the board. So now I've already programmed this. So now none of the LEDs are on in the standard state. And if I press one or the other, the one LED goes on. And if I press both of them, maybe, if I press both of them, then the other LED goes on. Right? So, and that's what I would expect. Maybe a better way is to put S and C into, or the inversion of S and C into a different variable, not S and not C, or active low S and active low C. I just decided to do it this way for, I don't know, fewer lines of code. But I think you'll agree that looks a bit more convoluted than what I had there originally. Okay. Now I wanted to do one other thing. Okay. And I have just forgotten exactly how to do it. Okay, so when you're designing stuff, whether it's logic or whether it's other electronics or if it's mechanical, you usually don't want to build it immediately. You usually want to verify that it's doing what you hope it's going to do before you push the button to build it. Right? So one of the things that Quarters lets you do is simulate what's happening. And in fact, even better, it lets you put a test bench together so that you can check, okay, if I give A and B as 0, 0, do I get the sum as 0 and the carry as 0? And then you can check all combinations of inputs give you the appropriate output. The way to do that is, and I'll show you this again when you need it, the way to do that is to go to the top level of in the project navigator, right click on the top level and go to settings, and if it's actually, and then go to EDA tool settings simulation and select, make sure that the right Model Sim Altera simulator is selected. That was what was set up in the new project wizard, right? And then go to compile new test bench. We don't have one yet, so we go to test bench and we say new. And I'm just going to say lab 3 test. Right? And I think that's all I need to do. Specify a test bench name. Oh, I've got to give it a name. I'm just going to say lab 3 test. Okay. I had to hit add, and now it's actually got it there. There we go. Can't find the test bench. Ooh. Ah, that's right. Sorry. I have forgotten that I have to add a test bench, and I've forgotten how to do that. Let me just quickly processing start. There we go. So it's processing start test bench template writer. There we go. Now that would have written a template. Let's have a look at where it put it. It put it in simulation model sim. So let's open that up. Eek, I don't want to do that. Let's open up that file, so it's not there, it's in simulation, model sim. No? lab3.vht. Ah, it hasn't. I'm just going to say all files, and there it is there somewhere. lab3.vht. Now, let's see if we can make that a bit bigger so you can read some of it too. So what this does is it makes an entity that is an underscore TST entity. Right? You'll notice that the entity has no inputs and no outputs. Right? This is just for simulation. Within the architecture then, it defines signals which are our inputs and our outputs so that we can measure them. Then it's saying create a component called lab3, right? And this port statement should match the port statement on the entity that we made. It will, it's automatic. You don't have to do that, right? I didn't have to do that. So there's the first piece. Then the actual VHDL starts, and the first thing it does is it creates an instance of the lab3 entity, and it's calling that instance I1. Okay. That entity has inputs and outputs, and our code here has signals. At the moment, there's no connection between the signals and the entity inputs and outputs. That's what this port map does. Right? It's a bit confusing because the inputs and the ports, or the signals and the ports, have the same name. Right? But this is just connecting signal A to port A, signal B to port B, etc. You could mix and match them, which would be a bit silly, but you could. And then there is no testing here at all. There's nothing happening. Right?
Question.
Yeah?
Is that the same assignment operator? Because on the other one it was less than something.
No. This isn't an assignment operator. This is a mapping operator. Right? Assignment was less than equals.
That's different.
Right? This one is equals greater than. So it's a mapping. It's usually only used in the map. Right? And it's the connection between there and there. In this lab 3, I wrote this. Right? But if I did this, right, if I took C and put it first, the code that would be output would be exactly the same. Because in this architecture, line 10 happens at exactly the same time as line 11. Right? There's no difference. It doesn't matter what order in this particular instance I put them in. Having an order is sometimes useful though. So VHDL defines the idea of a process. And the process, inside a process statement, so here's the begin of this process, here's the end of the process. Right? between those two begin and end keywords, the statements within there are sequential. Okay, so one happens before the other. So what I can do, I'm just going to ignore the init, that's just for initialization. I don't need to actually initialize anything in this one. What I can do here is I can say, let's just tab it in, right? So I can say set A to 0, set B to 0. And that will set input A to be 0 and input B to be 0. Then I can use the keyword assert, and I have forgotten exactly the format. There we go. There we go. So I can say assert S equals 0, report sum is not 0 for 0 input, and then severity failure. Let's just see if I can make that a bit bigger so I can, no, I can't make it bigger. Let's see if I can pull it out. No, I can't pull it out. See if I can kill that one. There we go. Right, so now I have a test. I have a test for the value of S. If this condition, S equals 0, is not true, then it's going to report sum is not 0. And it's going to give it a severity of failure. Right? If you've ever done any logging, there's often, debug information, warnings and errors. Right? They're the usual four. There's others, but right. So failure is one. I think I've forgotten what the available values are, but failure is usually a good one for tests. And then we can do the same thing for C, for carry. Right? We can say we have to check that C is 0, and we can say carry is not 0 for 0 input. And then because this is within a process, I can then do something sequential and change A to 1, in which case sum should be 1. Okay. And it's usually, if you're putting in error messages like this, it's good to make them all different. That way you know exactly which one went wrong. And I'm just going to do that and then change that to 0 and 1. right? And that should still be the same, but now B is 1 and A is 0. And let's just make that, and then when the last option is that, and if that's the case, we want the sum to be 0 and the carry oops. And that should be 1. So now I have a complete test of my truth table. Okay, so I should be able, hopefully, to compile everything. There's probably an error, but let's try it anyway. Next week, I'm going to ask you to do a step up and do a 4-bit counter, right? And it's going to be like the tutorial we did, except no funky changes, but I'm going to get you to do, first of all, I'm going to get you to do it in multisim with devices, and then I'm going to get you to do the same thing, but in VHDL. And just like we talked about earlier with the programming approach versus the bit approach, you'll find that the VHDL lets us do a little bit more of a programming approach rather than the bitwise approach that you'll have to do with the other one. Okay. Now I'm just going to check, once this is finished compiling, okay, looks like that finished. So I'm going to run the simulation tool and we'll see if it actually does anything. I did. It just took a while. Okay. So this is, let me see if I can get the preferences set up. Make the font a bit bigger. Tools, preferences, there we go. Let's just make the font, see if I can get the font to be a bit bigger. Maybe that did something, maybe not. Tree font, I think, is what I want. Just going to make that go to 14 point as well. Nope, that didn't work either. Okay, I'll figure it out later. So, what you oh, it did go. There we go. What you should see is if you've done the test bench correctly, you should get a work node, and your entity name and architecture name should end up being there. Right? And you should be able to go right click and say simulate. Okay, there's my signals that showed up, right, in my simulation were there in my simulation. And then what I can do eventually is I usually go that way, but you can just go to add wave. I get add wave selected signals, and that should pop up a separate window that has my signals on the left hand side, if we can figure out where that is. Where to go to. There it is. Right, so there's my signals on the left hand side, A, B, S and C. And then what I should be able to do is run them. And looks like I've done something wrong, because all of my signals are coming in as undefined, new. Okay. Where I want you to eventually get to is to be able to do this sort of thing with the projects that you complete. Not yet, it'll be a while, but that's the process, right? It's the old plan, do, review. Plan is doing the design. Review is putting it into, do rather, is putting it into VHDL or multi-sim or both. And then review is putting a test harness around it to make it testable, so that if you change something, you can tell whether it's broken. And the nice thing about automated tests is you should just be able to run it with a click of a button, or maybe several buttons, but it's better than me having to press buttons on the physical device to check that my truth table is fully correct. I mean, that's fun. I'm not saying you shouldn't do that, but you're better off being able, particularly with more complicated things than a half adder, right? A 4-bit adder now, or 4-bit counter. Now you've got 16 different operations, and being able to go through all of those is a bit more complicated if you're doing it by hand. Okay. Any questions? If not, that's all I wanted to get through today. Lab 4 is a little bit more work next week, so please prepare for it. I'll give you more time than I gave you for this one. Thank you for your attendance. And remember, there will always be some more participation work. Now that the first 2 chapters are over, it'll be a little less now that we're actually getting, but it's still